Welcome to your last calculus video. So high fives all around. Everybody got to the very last video. I hope everything's still going well. I know we're anxious and we're all stressed, but you're done after after this video in terms of math for now. So that'll be good. So remember, just always keep that light at the end of the tunnel. You're getting to the end. You're almost done. And today's not too big of a lesson. So some of you may have taken my advice after the last video, which was pretty long, just to chug ahead and just finish off this last video. So it won't be as long as that last one. The last stuff I have to show you with integrals is not a lot on top of what you've already learned. Okay, it's just a couple of small extensions. So the first thing I'm going to show you is how you actually determine C. So you saw in our last video from last week, or maybe you're watching it the same week, that all the answers of integrals you had to add C, because when you take a derivative of any constant you get 0. So there's no way that going backwards you're going to know for sure whether there was a constant or wasn't, and even if there was one you wouldn't know what it was. Well, that can be problematic if you're dealing with an actual application in which you need to find area under the curve, or you're trying to find something like our example of water going through the dam. We can't get accurate measurements unless we know where that curve is. So that plus C is going to dictate whether it shifts up or down. So how do we find C? So sometimes people call these initial value problems. Initial value kind of restriction that makes it sound like you have to have a starting value, and that's not really what it's about. Basically, if you want to find C, you need a point, okay, just a point on the curve. All right, as long as you have a single point to tell you, here's what the curve would look like, I just don't know where it would be, up this much, down this much. But if you have a single point on the curve, then you can lock it down, right? You can lock in where it would be. So that's really all that this extension is about for now. We've got one other thing I'm going to show you at the end, definite integrals, the other half of the coin. But those are the two things I'm going to show you, is how to determine C. So it's basically just, find your integral, and we're going to use a point to find that C. And I'm going to show you how you do definite integrals. What you've been doing up till now are called indefinite. You've been getting functions, not numbers. Definite integrals, you'll see that those allow you to actually find a numerical area under the curve. So we'll get to that in just a few minutes. If it's all right with these next examples, I am going to go through finding the the integral quickly, because I really just want to teach you how to find C. So I'm going to very quickly jot down how I'm going to find my integral. I'm not going to explain it really, I'm just going to do it. But certainly if you have any questions, just ask in the discussion. I just want to get through that part quickly since we just had a very long, almost I think 2-hour video finding integrals. So I'm sure you can find them by now. I'm just going to find them on my own, and then I'm going to show you what you do once you find them. Okay? All right. So I'm going to find y in terms of x. So I'm going to find the function of y. I know the derivative, which means I know the slope of the function everywhere. And I'm going to find the function with this slope, knowing that it passes through this point. All right, so again, if you can imagine when you find the integral, so y is going to equal the integral of 6x squared dx. So if this is the slope, I'm going to integrate it. So that's going to equal so y is going to equal 2x cubed plus c. All right, and again, if you want to pause it and have a look at how I did the integral, that's fine. But I'm not going to do anything new with the integrals that you didn't learn in the last video. So there'll be nothing new when it comes to the integrals, okay? So using what you learned in the last video, you should be able to get to that point. All right, so here's the new part. All right, I've got the function. Again, the problem is I don't know if that function should be basically, is it intercepting, if x is 0 at the x-intercept, sorry, not x-intercept, y-intercept. So at x is 0 at the y-intercept, is it cutting through 0, 1, 2, 3, -5, who knows, right? And that's the problem. When you're trying to find this function, where is it exactly? So this c doesn't narrow it down enough. But if I know that a little bit more about the function, that it's passing through 0, 2. So if I know that when x is 0, y is 2, that allows me to sub into this point and find my c. So if I use that, I get 2 equals 0 cubed plus c. I get the following. So I do some quick algebra. This really doesn't have anything to do with calculus per se. You're literally just subbing in a point into the function and you solve for c. So that gets us our final answer when they say find y. I now know the function is actually this. This is the true function with this derivative, but also passes through this point, because many functions can have the same derivative function as we saw in our first video. So this is the function. So this is how we determine c. We need the integral, so this is from the first video, but we need that extra bit of information, something about the function. All right, so they call it initial value problems. It doesn't need to be an initial value. Okay, you're going to find a lot of these are going to talk about what happens at 0, mostly because that tends to be the easiest point, even in real life, for us to determine. It's easiest to find out what happens at the beginning as we're starting something, as opposed to midway through. But it's not always, right? We could take a measurement at some point and find it, at 3 seconds or 5 meters in. So it's certainly possible. It doesn't have to be an initial value. You just need a point on the curve. All right, so if I apply that same technique here, so if I want to find f at x, I have the derivative. I know I want to integrate the derivative. And when I do that, I get the following. Right? But again, I actually want to find the full function, which in this case I can because I have more information. So if I take that one step further and say, when x is 0, fx is 2, which is what that means. This means when x is 0, fx is 2. So that's what I have. When I sub that in, oh, that x should be a 0. And plus c. So this is 0, this is 0, so c, just like the first example, it is also 2. So my actual function, f at x, is 3 over 2 x squared, 5x plus 2. So there's my function. Okay. All right, so I've got 2 more examples similar to this that I'm going to go through. But again, if you want to pause, if you get the idea, you're welcome just to try them out for yourself and then, listen to the video or check the answers. But I think the next 2 have substitution, so they're going to be a little bit longer to do the integral. One thing I do want to make a quick note of, because sometimes people go, oh, both times it's just been the y value, the zeros just cancel everything out and that's my answer. That's not always true. You're going to see in the next example that, the c is not just equal to the y value kind of thing. You shouldn't just make assumptions that everything's going to cancel out. It doesn't always. My 2 examples they did so far, because they've been, polynomials, they've just been, each term has had an x and x was 0, so it kind of worked out that way. But just, again, don't make assumptions that things are just going to cancel out. Not everything works that way. So you'll see in the next example that that's not true. So just be careful. Sometimes the first 2 examples, they're a little simpler. Everything cancels except the y values, and the left side ends up equaling c, but that was just these first 2 scenarios. Okay, you always have to go through and actually do a problem to be sure. All right. So how about a small application? The velocity of a robot arm, dS dt, is this. We may have actually done one similar to this, but we didn't have the initial value at one point. So we've got the velocity, the speed of the arm. What we're looking for is how it moves, displacement, okay? As a function of time, if we know that at 1 second, it's 1 meter behind kind of considered its starting point, okay? So its displacement is minus 1 meter at t is 0. Okay, so we know how we're going to have it move in terms of speed. What we want to know is how we can, figure out where it's going to be in terms of displacement after a certain amount of time. And from our videos on derivatives, we know that taking the derivative of displacement gives velocity. Well, if we have velocity, we know that this also works backwards. Okay, so that's something we want to keep in mind. If you remember from your videos before, velocity, acceleration, and displacement all worked as derivatives. So if you differentiate displacement, you get velocity. Differentiate velocity, you get acceleration. Well, it also works in reverse. If you integrate acceleration, you get velocity. And if you integrate velocity, you get displacement. And that's what we're doing here. So we're going to get the function for displacement by integrating our velocity. All right, so I've got my integral set up. I did quickly move the denominator up and give it a -2 instead of the squared on the bottom. And I'm ready to integrate this. So I am going to have to use substitution. So just quickly below, I'm going to jot down what I would use for substitution. So I've got u equal to t squared plus 4, what's in the middle. I know du dx is going to be, I should not use dx. The problem is sometimes you get in the habit of using x's so much you forget when you're not. So this is actually du dt, and the reason this is dt is because I've got t's here. So that equals 2t, okay? Which means when I go to sub in dt, I need to make sure I put in du over dt. So again, nothing new here. I'm just quickly going through the integral. Absolutely nothing new about what I'm doing in these steps. I just need to get to the point where I can find c. So again, if I'm going too quickly through the substitution, go back to the other video, please. And there I outline the steps in substitution much slower, and I'm going through every step individually. So if this is going too quick for the integral part, go back to the other video, please, okay? Alright, so those are the things I needed for substitution. When I put those in, 8t u minus 2 du over 2t. So that all cancels to make 4. And I end up just integrating u minus 2 du. Alright, so we end up with 4u minus 1 plus c. Alright, just keep that in mind because I'm going to turn my page over here because I'm out of room. Actually, I can do it over here. So I've got 4u minus 1 minus 1. So after all that simplifies, I get minus 4 over u plus c minus 4 over t squared plus 4c. Alright, so therefore, find the expression for the displacement, st. So there it is there. So there is the expression for displacement in terms of time. So now I not only know how fast the robot is moving at different times, but I also now know its displacement at different times of t. Now I can go a step further, and that's what these questions are about, is that I can actually go that extra step and find what C is by using the information given. So they tell me when T is 0, displacement is -1. So I am now definitely out of room, so I'm going to just turn the page over to do this. So I'm going to sub in those two pieces of information into here to get my C, and that'll give me my final expression for displacement. So -4. So ST was, so ST is -4, T squared plus 4 over C. Just make sure I got that right. Yep. And they also told me that S was -1 when T was 0. So I'm just going to verify. Yeah, okay. So one more little bit. Let's sub that in. See what we get here. -1, -4 over 4. It's -1 plus C. All right, what do we get for C? Well, -1, moving this over to the other side, that's +1. So I actually end up with C is 0. So there actually was no constant, and that can happen too. So with this example, I'm going to turn my page back over and have another look at that function. But in this case, there was no constant at all. So we had plus C, but we didn't actually need it. That's fine. We still have to write it when we initially do the integral, because that's our issue, right? We don't know whether there was supposed to be a constant or not. So until we know what C is, we have to include it, because it just means constant. It doesn't mean, you know, there has to be a number there. The number could be 0. But until we know, that is, you know, that is what we have to use. But now we know that C is 0. So the function for the displacement for this robot arm that moves with this type of velocity, so the function is actually just this here. So there is no C. That is the correct function for the displacement. All right. So I have one more example. Again, hopefully that's hopefully this is making, I know I'm going a little faster through the integrals, but again, I hope this is making sense. I'm not teaching you anything new to do with the integrals. These applications aren't meant to be, you know, like the optimization ones. You were probably feeling, you know, the optimization ones were hard for sure. You know, that's not what these ones are. When, again, for those that are going to go on to Math 20, that's where I think you're going to get to see some of the more involved applications. Here, it's just about, I think the way I explained it to you when you first learned calculus, the calculus you're learning in this course is like learning your letters, okay? You know, you can't learn how to spell words and write sentences and essays until you learn what the letters mean. So that's what this course is really for you. I just want you to see what a derivative is on the most basic level. It's, you know, slope of a curve. Can you do a couple derivatives? You get the idea of how we get them, even though it's not all of the types that we, you know, that exist. It's just really giving you that, you know, that little bit of a foundation, so that you can, you know, you can do more complicated things. Even if you're using computers to do it, you still want to at least know just that, really that blanket bit of foundation. That's what we're looking for here, okay? So I hope this is going all right so far with integration. We got one more example for initial value. So here we go. Same thing, I'm just going to get the integral really quick. So we are looking for an expression for t. Okay. Well, they didn't give me an expression for t, they gave me dt, and I know that means the derivative. So the rate of change is given by this, but I want the initial function. I don't want the slope function, I want the function itself. So that means integration to me. So integration, to get back to my function, if I have the slope is found by differentiating, the initial function will be found by integrating. So I've got this working like that. So I'm going to use r here. So again, because I'm using r, I need dr. So I have to use substitution here. So u is r plus 1, du dr is 1, so therefore du, dr is equal to du. So there won't be much substituting there. All right. So when I go ahead and I substitute, I might just pull that 4,500 out. So when I substitute, I get u minus 3 du. It wasn't much to do. The u subs in, and the dr is equal to du. So yeah, that was pretty quick to substitute. When I integrate, I get 4,500 plus 1 and c. So let's see here, 4,500, cancel the negatives, divide by 2, so we get 2250, and then the u minus 2, I want to substitute u back in, which is r plus 1, minus 2 plus c, and we'll do one more. Let's put it all over, just like that. Okay. All right, so again, there's my integral. I know I went through it super fast, but again, this is under the assumption that you have already watched the first video and you are relatively comfortable with doing integrals. You don't have to be able to do them that fast. I just want to get the integral out of the way so we can move to the next part, okay? So if you're having trouble with the integrals, remember you can always just stop the video and then, you know, even right now as I'm speaking, press pause, look at what I did, see if it makes sense. But if you're having trouble with the integrals, go back to the other video, please, okay? All right, so that is your function for temperature. You were given the rate of change for the temperature. We want just the temperature function. Again, we are going to use what was given, though, to go a step further. So as long as you know something about the temperature function, that when r is 0, it's 2,500, for example, that will allow you to find c. Okay, so again, even though I think all the examples I've done, it's been for an initial value, so an r is 0 or t is 0. Again, it doesn't have to be. As long as you know any point on a curve, you can find that constant. So we're going to do it for t is 2,500 and r is 0, though. So 2,500, I need 250. 0 plus 1, and c. All right, what do we got here? So on the left side, nothing to do. On the right, we get this over 1 squared. Well, that's just that. And when I move this over, it changed signs, so it subtracts. So I end up with 250. And there's our c. So our temperature function is actually this. There it is. Okay. So in all of the ones you've been doing up until now, you were just writing plus c, and that was fine. That's not wrong. You know, that's the expression as you know it. So until you have a little more information about the curve, a little more information about a point on that curve, you have to leave it as c. But as soon as you do have that extra point, you can find c. Okay. All right. So, the very last thing I'm going to show you is how you deal with a definite integral. So, as I mentioned, what you have learned so far has been the finding of functions. You haven't really been finding numerical values like areas under the curves. But you can. And again, there's not a lot new to this part. So recall this, what we saw in the PowerPoint was that adding all the triangles together will give you that area under that curve. And it was a limit, and then we went even further, and you would have saw this, all right? Now you may not have noticed, but in the PowerPoint, it looked like this. You've been writing integrals the whole time, like this, okay? But a definite integral, the reason it's a definite integral is it adds in these boundaries, okay? So these are boundaries to tell you where do you want me to find the area under the curve, right? Because a curve goes on forever. So when we do an indefinite integral, there's no numbers on it, meaning that you're just finding an expression to show you the curve that, exists everywhere. When you want to find something more definite and you want to find area under the curve or volume or work or pressure, and you have specific interest in a specific section, because it is possible to go do it for infinity to a negative infinity, but likely for your application, you'll have a bounded area. These two numbers here tell you between where do you want that area found. Where do you want me to add the area together to get the answer? So those are definite. Now, to actually do it, again, there's not a lot extra that needs to be done. Essentially, you're going to find the integral, same way you did it before. Again, there's no new methods. You're going to do exactly what you've done, either power rule or substitution. And you're going to sub in the value of your top bound, b, the value of your bottom bound, a, and you're going to subtract them. Okay. The only thing really to be careful of here is watch your order. It does matter. Make sure it's b minus a, top minus bottom. Okay, so we call those the limits, the upper limit and the lower limit. So it's always got to be upper limit minus bottom limit. Okay. Yeah. Otherwise, that's what it's about. So I thought we could do a couple examples, and that'll finish everything off for us for the semester. All right, let's try the first one. So 0 to 2, 3x squared dx. So here's how this would be different than the ones you've done so far. So I'm still going to perform my integral. So 3x squared is going to be 3x cubed over 3. Now here is where we would add a little bit more to it. So here I've just done the power rule. I've added 1 divided by 3. I can see this is going to cancel, but we'll do that in a minute. So here's what we would add to it. There's usually a little line that goes to the side. Okay, and that little line is saying you've found the integral. If you want to take another step or two to simplify, go for it. So you are going to be evaluating. I do recommend simplifying before you evaluate. It will make it easier. But that little line on the right is saying you found the integral. When you're done, whatever it is you're going to do next, if you're going to take a couple steps to do it, when you're done and ready, evaluate from 0 to 2. Okay, so 2 and to 0. So I'm going to do one more line and cancel. And I'm going to evaluate from 0 to 2. So again, be careful of your order. So you want to make sure you do upper bound first. Okay, so upper bound first, then the lower bound. Top number minus bottom number. All right. Sometimes we have negatives in here, and people always do the positives first instead of the negatives, or they do a weird order to it. So just make sure it's top minus bottom. Okay. All right, you just sub it in. So 2 goes in for x minus 0. Our answer is 8. So if you were to graph that, and if you want to give it a try, you could. I won't pull it up on my computer. It's kind of harder to do when it's not face-to-face in class. But if you want to pull up something like desmos.com and graph something like 3x squared, I think you'll get something. Well, this one might not be the best example to try, but try something even like, I don't know, maybe 3x or 2x, something where you get a straight line, and you'll be able to count the area under the curve, and you'll see it'll match your answer, because that's what you found here. So you found that there's 8 units under the curve of 3x squared. Okay, So when if you graph 3x squared, if you count the number of units underneath between 0 and 2, you would get 8. Okay, you found area under the curve. All right, number 2. So we're going to integrate over 1.2 to 1.6 of a function that is 5 plus 6 over x4. Alright, so the first part is same as usual. We are going to integrate. I'm going to set it up first though. So I set it up to use the power rule, and I go ahead and integrate, and I have 5x plus 6 minus x minus 3 minus 3, and between 1.6 and 1.2. Alright, a little bit of simplifying gives me the following. Alright, so there's the integral part. So nothing has changed up till now, except I'm adding, I've got the bounds here, and then I've got these extra bounds on the side to indicate I need to evaluate. So I'm adding those little extra bits for the definite integral to show that I'm evaluating. One thing you may have noticed from the first example, and maybe this one too, is maybe you're wondering, where is C? Why haven't you been writing C? You said a whole bunch of times in the first video that we always had to write plus C, and now you're not. The reason I'm not writing it, and I'll make a little note up here at the top for you, where is C? Where is it gone? If I integrate something like 2x, let's say, all right, and I integrate the function, I want to evaluate between 0 and 1. When I integrate that, I get x squared. And if I add plus c, like I normally would, and I say, okay, I'm going to evaluate that from 0 to 1. When I do that, I get 1 squared plus c. Then when I do it for 0, I get 0 squared plus c. What happens every time you do a definite integral with plus c is it always cancels. Plus c minus c. Plus c minus c. That happens every time in a definite integral. So because that happens every time, we no longer write it. If it's a definite integral, if it's a number you actually have the bounds for, you don't need the plus c anymore because the function has canceled it out on each bound. So we don't have to write it when it's a definite integral, okay? But you have to have it with indefinite. So when there are bounds, you don't need the plus c, okay? But when there are not, you need that because you're trying to find, it's basically based on what you're trying to find. An indefinite integral finds the function, and the function needs the plus c. But indefinite integral, finding area under the curve, doesn't need the plus c anymore because where the bounds are being found, they end up canceling out because they're constants on both sides. Alright, so that's why you're not seeing plus c, in case anyone had caught on to, that seemed to be missing. Alright, so I need to find this 1.6 and 1.2. Try to use brackets. I always used big giant square brackets. I use that to help me keep straight where I have this part of the function and then where the minus is, because you really have to watch that minus. It's very easy to miss it and not have it expand all the way through. So I always use these big giant brackets to help me keep straight what is in each one. So I do something like this, and then I evaluate each bracket and then subtract. Okay? That way I know I'm not making any mistakes with my order of operations, and I'm coming out with correct answers. So I'm going to evaluate the first one. And I'll do the second one as well. Alright, so I am getting decimal answers, so it's not going to be perfect unless you use some kind of program that's using the full decimal places. But I've got a good idea of what my area under the curve is. It's 2.672 units, alright? And if it's an application, you'd have actual units, but that's how much is between the curve, area under the curve, between 1.2 and 1.6. Alright, so the main thing when you do the evaluating, again, the only thing new here is basically, from here down, this is the new stuff. All the integration up till now, again, completely the same. So you're evaluating at your upper bound minus your lower bound. Again, please make sure you do something to keep the two pieces straight. You really want to watch this negative here. Again, it's very common to have students kind of subtract this and then subtract this, not realizing that this makes this positive. So my suggestion, again, is to kind of keep some nice big giant brackets, do one piece and then another, and then you can subtract the two. All right, again, it'll eliminate some headache for order of operations. All right, let's try again. All right, we're going to do 4 examples and the 2 last applications. Alright, so again, integrate, nothing new there. Just go ahead and integrate. So 3x6 over 6 minus 2x4 over 4. Evaluate at 2 and minus 1. Alright, if you want to do some simplifying first, you can. If you don't want to, I mean, it's not going to hurt anything very much if you have 3 over 6 or 1 over 2. I will, because it's good practice. It's a good idea, I think. Alright, so I have my simplified version. This is what I'm going to sub them into. Again, just like the last one, really just be careful what you're putting in. So you're going to have 2 to the 6 over 2 minus 2 to the 4 over 2 minus bracket. Now this is minus 1 is my other bound. So minus 1 to the 6 over 2 minus minus 1 to the 4 over 2. Alright. Be careful when you put these in the calculator. Remember, they have to have brackets on them before you evaluate. Otherwise, you're going to get minus 1 to the power of 6. So you're going to get negative 1. It's not supposed to be negative 1. Okay, these both actually come out positive. So make sure you've got those brackets in your calculator. Alright, so over here we've got 2 to the 5 minus 2 to the 3. 24 minus negative 1 to the power of 6. Like I said, it should be positive 1, so make sure you've got that bracket on there. So we're going to have 1/2 minus 1/2. I think we're getting 0 there by the looks of it. So 24 units. All right. Hopefully that one all right. Again, just small things. Again, nothing's really new for integration. You just got to sub some stuff in. Again, just be careful. The most common mistakes I see are really have to do with this minus sign here, not either not using brackets well and doing things too quickly, so you kind of end up just putting it all in one and making a mistake. That or usually negatives. Again, problems with negatives in the calculator, brackets in calculators. So just go slow and just put things in properly, okay? All right, one more. All right, substitution 1. So u is going to be 3x squared minus 1. Du dx is 6x. Alright, so if I go ahead and do my substitution, I end up with x is canceling, the 4 and the 6 reduced to 2/3, u cubed du. So we end up with u4 over 4. And I'm going to simplify, so I get 1/6, so I get u4, 6, 0, 1, and 3x squared minus 1 over 6. And I'm going to evaluate. So there is one thing I want to mention at this point. So again, up until now, none of what I've done so far is new. This is all still just substitution. The only thing new is I have numbers on my integration sign, and I'm putting numbers beside to say I'm going to evaluate when I'm done. There is one thing I should mention in case you're using another resource other than my videos. Maybe even the textbook might do it a little bit differently. So in really strict calculus, technically when you sub in du, when you put in u and du, you're supposed to adjust the bounds, okay? Because these bounds are for x. So you're supposed to figure out, when x is 1, the bound here should be 2. So you're supposed to change the bound to 2, and when x is 0, you're supposed to change it to -1. So when you put u in here, you're supposed to change these bounds. I don't. I don't want to say what I'm doing is wrong. I don't think it's not wrong. It's just so much more to remember. It's easy to forget. You're more likely to make mistakes doing that. I just don't feel like it's a necessary thing. But here's the catch to it. Since we aren't going to change these bounds, so these are going to remain our original bounds, even though we changed it to u. It's even more important then that you make sure you sub x back in, okay? Because you can't stop here, for example, and put in x is 1 in for u, because that wouldn't be correct. So it's really, really important that you make sure you take that extra step and put x back in, because these bounds are very specific for x is 1 and x is 0. And if you don't have x in the integral when you're the final answer of your integral, then you're not going to have the correct answer. Okay? So if you are looking at some other examples, and maybe they do happen to change the bounds, because what could be done, and again, you don't have to do this or even understand this because you don't have to do it, but if you do change these bounds to reflect u, that means you could stop at this point and sub in, okay, if you change the bounds. But again, the chances of us remembering to doing it or do it correctly, I've found in my experience it isn't great that most students will actually do that. So just to make things simpler, to make life easier, the bounds are going to be kept the same. The x bounds are going to remain. Just make sure when you're done, before you start putting those numbers in, that you have x back in the function, okay? So if you do happen to be looking at other resources and wondering why on earth they'd be changing bounds randomly, technically the bounds do change when you put in u, because these are bounds for x, but again, it's just so, it just feels needless. It feels like extra work that doesn't need to be done. As long as you remember to put x back in, you're fine. So why do the extra work, okay? Hopefully you've kind of already started to train yourself with all those videos before for substitution to make sure your last step is to put back x in anyway. And if you have, then this is going to be, you're going to be fine with this. So that's the only thing I just wanted to mention, is if you happen to see a little bit of inconsistency, maybe with another book or a resource, we're not doing anything wrong. We just have to be particularly careful to make sure that our x comes back out, okay? All right, so let's evaluate. So I'm going to sub everything in there. I did that really quick. I'm going to make sure I did it right. 3, 1 squared minus 4 minus 1 all to the 4 over 6. That looks good. That looks good. Okay. So one final note before we finish off this example. We'll do those last two applications in the notes there. Something I've seen can be a common mistake is that sometimes when students get 0 as their other bound, so they get 1 and 0, for example. The very first example we did, I think, had 0 as one of the bounds, so we got 2 to the 3 minus 0, so the second bound didn't have anything. That can happen, you know, often enough, and sometimes people get the misconception that when one of your bounds is 0, this must automatically be 0, right? You know, if you're thinking, well, if one bound is 0, you know, I plug 0 in, it's going to be 0 anyway. That's not always the case. Never again, don't make that assumption that just because it happened a bunch of times already or it happens a lot, that it's always going to happen. You can see actually here, yes, this part is going to be 0, but you're going to end up with minus 1 to the 4. Okay, so you're not actually going to end up with 0 for this whole second piece. It can sometimes be a bad habit that people just say, oh, you know, this must be 0 because I used 0. That's not always true, right? So just make sure you do the problem completely, don't make assumptions. All right, so sub it in. We got 3 minus 1, 2, so 2 to the power of 4 over 6 minus, and we're going to have minus 1 to the power of 4 over 6, and I'm going to evaluate that in the calculator real quick. So I should get 16 over 6. .5. All right. Sorry, I'm just double checking my answer here. Something looked a little off, so I was trying to see if I'd had a bit of a mistake somewhere, but I don't see one, so maybe I am okay. No, it looks okay. All right. Hopefully I'm not missing it. I don't know why, but I just had this feeling like I'd made a mistake. So that looks okay, though, I think. So we're done with those. I hope that worked out. Again, I hope it wasn't too big of an extension onto what you've already learned. We just got those two examples on the sheet that we're going to do, but again, if you've got the idea, you're welcome to stop the video here and just finish off those last two and check the answers afterwards. The two I'm referring to are these two here. There were two applications on the notes, one about work and one about water flow. So we're just going to quickly do those here in the video, but again, if you've got the idea, you're welcome to stop here and you know, be done. So but yeah, if you do stop here, good luck with everything, and stay safe, stay healthy, and you know, we'll see at some point in the hopefully nearest future when we ever get back to school. All right, good luck. All right, if you're still with me, we're going to do these last two examples. So the work in foot times pound is winding up a 8-foot cable. The work is defined as the integral from 0 to 80 of the following function. Find the total work. So this was one of the more simpler examples I could find. There are some, you know, as you do learn more applications of integrals, there's ones about work and pressure, springs, like I said, volume. There's quite a few actually, and then they do get pretty interesting. This was just one I thought we could do. It was more on the simpler side because we haven't learned a lot of advanced techniques in this course. So but I wanted to show you how you can determine something like work. Okay. So we're going to integrate from 0 to 80, 1000 minus 5x dx. Right, again, I'm going to do the integral part pretty quickly. So 1000x minus 5x squared over 2 from 0 to 80. All right, I'm going to evaluate. Alright, now I don't want to make assumptions, but I can tell that this second piece is going to be 0. Just with a quick glance, I can see, 0 and 0, so that is going to be 0. Just again, don't make assumptions, but, if you look ahead and you can see, this times that, and, minus that, it's all going to be 0. I don't need to evaluate that. I can see it's 0, so that's gone. And I get 64,000 feet times pound, okay, which is my answer, right? Again, if you want to try the next one on your own, you'll find the answers just there in brackets as well, okay? But yeah, there's that one. So it's not too hard to actually find, our areas in the curve. All right, one more. Water flows from the bottom of a storage tank at a rate of RT 200 minus 4T. This is liters per minute. And it's going to do that from 0 to 50 minutes. So the assumption is, in 50 minutes it's going to be empty. So find the amount of water that flows from the tank during the first 10 minutes. So you can imagine a tank, it's got water in it and it is flowing out of the bottom. Maybe in the 50 minutes it's empty. That's why it's between 0 and 50, is after that it's empty and it needs to be refilled. How much water, though, have you removed from the tank after just the first 10 minutes? So let's see. Well, one of the things we learned in that first PowerPoint was if we know the rate and if we know the time frame in which we want it to happen, we can figure out amount, right? Because rate equals amount over time. So if we want amount of water, it should equal rate times time, otherwise known as area under the curve. So if we want to find the amount, we're going to do the area under the curve of the rate function. Now they want us to find it for a specific time frame. How much has gone through in the first 10 minutes? So from 0 to 10. So if I integrate, I get the following. Right. I skipped a little bit ahead here. This would have actually been 4t squared over 2. I knew that ahead, so I know it's 2 squared. I also just knew that, if I want to take the derivative to get 4t, 2t squared is what I would use. So I actually did the antiderivative in my head really quickly. So again, if you just use the power rule, you'll have t squared over 2. 4 over 2 makes 2. So I just went a little bit ahead there. All right. If I evaluate at 10 and at 0. Again, just with a quick glance here, I can see this is 0 minus 0. That's gone. So I end up with 2,000 minus 200. But I'm just going to double check. 1,800 liters. So 1,800 liters has left the storage tank in the first 10 minutes. Okay. So yeah, there is how you can also get your numerical area under the curve. Alright, so if you didn't stop the video and you watched these last two examples, alright, then you're now officially done. Those are all the examples I have for you. So you can do some practice. Like I said earlier, good luck, and hopefully we'll see you back on the campus next year. Alright, good luck. Stay safe, stay healthy.